Hello, today I'm going to start a new series aimed at A-level students of physics. A-levels, or advanced level, in England are taken by those students aged 16 to 18 just before they leave school and go on to college or university. Today we're going to look at classical mechanics, which covers all of these items listed here. It is called classical mechanics because it doesn't take into account Einstein's theories of relativity. First, we look at Newton's laws of motion. The first law says that an object will continue in its state of rest or uniform motion unless acted upon by an external force. And what that means is that if there is an object at rest, then it will stay at rest forevermore unless there is a force that comes along and causes it to move. Alternatively, if a body is travelling through space at, say, 20 miles an hour, then it will continue to travel at 20 miles an hour for the rest of eternity through space in a straight line without deviating and without the need for any more energy or power to do so. Now, this seems at first sight to be contrary to our experience on Earth, because if, for example, you roll a ball along the surface of the Earth, eventually it slows down and stops. And the reason for that, of course, is that it is going through air, and there's some turbulence in the air which creates a force that slows the ball down. And of course there's friction with the ground which creates a force and slows the ball down. So we are used to things slowing down. But according to Newton, if there are no forces, then it won't slow down. It will continue forevermore without any additional power. Newton's second law follows on from this by saying that if you do want to change the speed of something, then you have to apply a force. And this gives us one of the most common equations that we will find. F equals ma. F is the force, m is the mass, and a is the acceleration. It says if you want to change the velocity, which a change of velocity is acceleration, if you want to change the velocity of the mass, you have to apply a force which is equal to the mass times the acceleration. If we look at the units of this, we would say that the units of force are mass, which is of course kilograms, times acceleration, which is meters per second squared. But that's a rather clumsy form of units, and so that is usually replaced by the units called the Newton. Force is expressed in newtons. Newton's third law is commonly expressed as to every action there is an equal and opposite reaction, which means that if I lean against a wall and exert a force on that wall, the force exerts an equal and opposite force on me. When I stand on the ground, I exert a force on the earth, and the earth exerts an equal and opposite force on me. In other words, the force by body 1 on body 2 is equal to the force by body 2 on body 1. We're going to look at a couple of definitions. First, we're going to define velocity as the distance, which we usually represent by the letter S, divided by time. If you travel 60 miles in 1 hour, then you can say that your velocity is 60 miles per hour. What is the difference between velocity and speed? Well, velocity is a vector, and a vector has magnitude and direction. And it's the direction point that separates out the vector. If you want to define a vector, you have to say not only how big it is, but also which direction it's pointing. So velocity is 60 miles an hour north, whereas speed is a scalar. It has magnitude, but it doesn't have direction. So you can have a speed of 30 miles an hour. We have no idea which direction you're going in, but if you have a vector, then we know both the magnitude, 30 miles an hour, and the direction, north. We're also going to define acceleration. Acceleration is the rate of change of velocity. So if we start with velocity u and we finish with velocity v, then the difference between them is the change in velocity. And the rate of change of velocity is v minus u divided by t, the time it takes for that velocity to change. That is the rate of change of velocity. And the units for this are obviously velocity, which is meters per second, divided by time, which is also measured in seconds. So this is meters per second squared. And now we can start to derive some useful equations. From this equation here, you can see that if we multiply both sides by t, we get at equals v minus u. And if we bring u on the other side and rearrange, we can say that v equals u plus at. And that's our first main formula. It says that if you start with an initial speed, or more accurately an initial velocity of u, and you accelerate at a rate of a for a time t, then your new velocity will be v. We can plot velocity against time. This is velocity, this is time. We start at velocity u and we finish at velocity v. And we do that in a time t. And that means that the velocity will go from here to here. This is time 0, this is time t. And so that's what the graph looks like. You started at velocity u, you finished at velocity v, and it took a time t to get there. What is the distance that you've travelled? Distance, as we've said, is represented by the letter s. And the distance is the area under that curve. And what is the distance under that curve? Well, what is the area under that curve? Well, this area here is simply u times t. U times t. The area of the triangle is half the base times the height, which is half of the height, which is v minus u, times the base, which is t. And that, we say, is s, the distance. The distance is the area under the curve, which is that oblong plus that triangle. But from this formula here, v minus u is at. So we can put at here. And that means that we get that s equals ut plus a half at times t, which is at squared. And there's our second major formula. That the distance travelled is the initial speed times the time at which you travel at that speed, plus half of the acceleration times the time squared. Now let's go back to this equation here, and we're just going to square it. And that gives us that v squared equals u plus at all squared. That was from that formula there, we get this here by squaring both sides. And that is u squared plus 2uat plus a squared t squared. Well, we can rearrange that to say that v squared is equal to u squared plus 2a into, well, ut plus 2a into this is half a t squared. But ut plus half at squared is s. And that gives us our third formula, v squared equals u squared plus 2as. Now let's take that formula, v squared equals u squared plus 2as. And remember that we've already identified Newton's second law, which says that F equals ma. which means that A is F divided by M. So we can substitute that into this equation. V squared equals U squared plus 2, and instead of A we're going to put F over M times S. And now let's just work that through. V squared minus U squared is 2Fs over M. M into V squared minus U squared equals 2Fs. M over 2 V squared minus U squared equals Fs. And that means that a half mv squared minus a half mu squared equals Fs. This is the kinetic energy that you end up with. This is the kinetic energy that you started with. And the difference between them is the difference in energy is the work done. And the work done is the force times the distance through which the force has moved. And so energy and work have units of force, which is newtons, times distance, which is a metre. So the units of energy and work are Newton meters, but we give them another name. We call them joules. Now we come to momentum. Momentum, which is often labelled by the letter P, is mass times velocity. And that would be in units of kilograms for the mass times velocity, which is meters per second. So the units of momentum are kilogram meters per second. And force, as we shall see, is the rate of change of momentum. Now, what is the change in momentum? Well, the change in momentum is the difference between the final momentum, which is mv, take away the initial momentum, which is mu. That is the change in momentum. But we need the rate of change of momentum, which is mv minus mu over t. That gives us the rate as it changes with time. And that, of course, is simply m into v minus u over t. But what is v minus u over t? That is simply acceleration. And so we get that the rate of change of momentum is mass times acceleration, which of course from Newton's second law is force. Now, momentum is always conserved, provided that there is no external force. So if, for example, you have a body of mass m1 travelling at velocity v1, and it hits another object of mass m2 travelling at v2, obviously v1 must be bigger than v2, otherwise it's not going to catch it up, but it catches up and it hits it, and the two stick together and they produce a kind of combined object. M1 and M2 are now stuck together, travelling at a new velocity v3. And what you can say is that momentum is conserved, which means that the momentum on this side is m1 v1 plus m2 v2. That's the momentum of that body, that's the momentum of that body. And that equals, because momentum is conserved, the momentum of this body, which is its total mass, m1 plus m2, times its new velocity v3. We can use this, for example, to consider the situation where a cannonball is firing. Now, a cannon on its own with the ball inside has no momentum. It isn't moving. But once the cannon is fired, the ball will come shooting out at velocity v1. And let's say it has a mass m1. The cannon, which has a mass m2, will then have to what they call recoil at a velocity v2 in order that momentum shall be conserved. The momentum beforehand was 0 and the momentum afterwards must be 0. And that means that m1 v1, that's the mass of the cannonball times the velocity of the cannonball, must equal m2 v2, that's the mass of the cannon times the recoil velocity of the cannon. I now want to consider elastic and inelastic collisions. What does this mean? An elastic collision says that the energy is conserved in the form of kinetic energy. An inelastic collision means that the energy may be conserved, or indeed will be conserved, but not necessarily in the form of kinetic energy. Energy is always conserved, but it can be, as it were, lost in the form of heat or sound or light. What this means is that if you have an object m1 travelling at velocity v1 and it catches up with and hits an object of mass m2 with velocity v2, and that produces two separate bodies, one still mass v1 but travelling at a new velocity v3 and the mass m2 travelling at a velocity v4, then you can always say that momentum is conserved, which means that m1 v1 plus m2 v2 equals always m1 v3 plus m2 v4. That is conservation of momentum, and that always happens. What you cannot necessarily say is that energy, or kinetic energy, which half m1 v1 squared plus half m2 v2 squared, does not necessarily equal, it might, but it does not necessarily equal half m1 v3 squared plus a half m2 v4 squared. And why may that not be the case? Because some energy may have escaped in another form. For example, when these two bodies collided, maybe they made a sound, maybe there was some heat, maybe there was some friction, and all of that would be energy that would be lost from this equation. Energy is always conserved, but not necessarily as kinetic energy. A good example of energy changing its form, but nonetheless being conserved, is if you jump off of a diving board into a swimming pool. Whilst you are standing on the diving board, which is at a height h above the pool, then you have what's called potential energy. You're not moving, but you have potential energy, and that equals your mass times the gravitational force caused by Earth's gravity times the height above the swimming pool. But when you get down and you're just about to splash into the water, all of that potential energy has been converted into kinetic energy, which is a half m, your mass, times your velocity squared. And those two will be equal. mgh equals half mv squared. The m's cancel, and so if you take gravity multiplied by the height above the swimming pool, that will be the half of the velocity squared with which you enter the water. So the key message is that momentum is always conserved. Energy is also conserved, but not necessarily in the same form. Kinetic energy specifically is not always conserved. Now I want to look at impulse, which is the change of momentum. Now you'll remember that force was the rate of change of momentum, which is mv minus mu divided by t. That's the rate of change of momentum. What is the change in momentum? Well, that's just mv minus mu. And mv minus mu divided by t is the rate of change of momentum. So in other words, mv minus mu, which is the impulse, is equal to force times time. And the units of impulse are obviously going to be force times time, which is Newton seconds. So if you've got an object which is travelling along, let's say it's got a mass m1, it's travelling at velocity v1, and it hits a brick wall, which for all intents and purposes is immovable, that will come to rest. It will still have mass m1, but its velocity will be 0. And the impulse will be the change in momentum, which is mv minus mu, but that's 0. So it's just mv. And that equals force times time. Now you can imagine that if that's a car, mv is going to be a constant, the mass of the car times its initial velocity. But the force that will act on the driver of that car will critically depend on how much time it takes for the car to stop. If the car stops almost instantaneously, if t is very small, then F must be very large, and that very large force is what is dangerous. But if you can make t last a little bit longer, if t is larger, then the force is reduced, and therefore the impact on the driver is significantly reduced. And that's the purpose of crumple zones in cars, that actually as the car crumples, it takes a little bit longer to come to a halt, and that increases the time and therefore reduces the force on the driver. And that can make all the difference between whether the driver gets out of the car or not. I now want to move on to look at power. Power is energy or work per second. That's not energy divided by work, it's energy or work per second. In other words, energy, which is measured in joules, and time is measured in seconds, power is measured in joules per second, or we call it watts. So power, capital P, is work divided by time, but you'll have remembered from before that work is force times distance. So now we can say that power is work, which is force times distance, divided by time. And distance divided by time is simply velocity. So power is also force times velocity. Now we spoke earlier about velocity being a vector. Force is also a vector. And so you need to take that into account when doing any calculations. Let's suppose that I'm dragging something along the ground. I will need to apply a force because friction will otherwise stop it. And here I am, and I've got hold of a rope, and I'm pulling this object, and I'm applying a force F. But is that the force that will cause this object to move? Well, no, because that force is at an angle, and that angle is theta. And the actual component of the force that's moving in this direction is F cosine theta. There is also a force, or a component of a force, moving in that direction, which is F sine theta. And if it's too great, it will simply pull this up off the ground. So what I want to do, if I want to be the most efficient I can be, is to make sure that this rope is as close to being parallel with the ground as I can get it, because then all the force is going into moving this object in this direction, and none of it is going into lifting it. It might be worthwhile just quickly covering here the rules for adding and subtracting vectors. If you have an object on which there are two forces, F1 moving in that direction and F2 in that direction, then the rule for finding out the resulting force is to add the two together. And when you add forces, you always add head to tail. This is the head, this is the tail. So you take F1, and then you take F2 and you put the tail of F2 to the head of F1. And the resultant force caused by adding the two together, F3, is just that line there. By contrast, if you want to know the difference between force F1 and F2, well, then you just have tail to tail. You leave them as they are, and the resultant force, which we'll call F4, is the difference now between F1 and F2. That's the basic rule for the addition and subtraction of forces. And then finally, in this review of classical mechanics for A-level physics students, I want to look at moments and torques. A moment, which we often describe as capital M, is the turning effect of a force. Let's suppose that we have a bar with a pivot where it's actually fixed to the ground. If I apply a force here, what will happen? That will spin around this pivotal point here. And the moment of the force is the force multiplied by the distance, which we'll call A, from the, as it were, turning point to the point at which the force is applied. So the moment of the force is the force times the distance. Now you can have moments of forces that balance, and the best example of that is a seesaw. Here is a seesaw, here is the pivot point, and here are two people. They should be sitting on the seesaw, but rather foolishly I'm going to have them standing on the seesaw. This person has a mass m1, and therefore will have a force of m1g. The way you find forces, remember, force is mass times acceleration. The acceleration in respect of a person on a seesaw is simply the acceleration due to Earth's gravity, which is g. So the force is mg. So for a person of mass m1, the force is m1g. For a person of mass m2, the force is m2g. Now let's suppose that the distance in this case is A and in this case is B. Then the seesaw will not move provided the moments of those two forces are equal. In other words, m1g times A has to equal m2g times B. The force times the distance on one side has to equal the force times the distance on the other side. Otherwise, the seesaw will move up or down. And you'll see that the moment of a force is force times distance, and that is Newton meters. It's essentially got the same units as energy. A torque is like a moment, but it essentially is the moment of a force applied on both sides of the turning point. So let's suppose the turning point is here. Here is, let's say, a bar of metal, and we apply a force that way and a force that way, and they are equal forces. And the distance between the two forces is distance d. This might be if you're trying to get off the wheel nuts of a car tyre, and you will apply a torque, which is often represented by the letter tau, and that equals the force times the distance d between the two forces. And you can see that for any given force, the torque will be increased if d increases. So if you have a particularly stubborn wheel nut that you have to get off, you want to get a wheel brace that has the biggest distance that you can apply the force to, because the bigger the distance, for the same force, you will get a bigger torque on that wheel nut and you're more likely to shift it.